So the overarching goal for today's experiment is to utilize two-dimensional motion equations in order to predict the impact location for a projectile that's launched at an angle above the horizon. This is the projectile launcher. You'll note that it is not at an angle above the horizon, and that's because we'll need to do this experiment in effectively two parts. The first part will be to determine the muzzle velocity of this launcher. It's right now unknown. And the second part will be to take that muzzle velocity and use it with the two-dimensional motion equations and the quadratic formula in order to predict the impact location of a projectile at an angle above the horizon. So let's talk about that first part, that is determining the muzzle velocity of the projectile launcher. This is important, as I said, because we're going to need to know this muzzle velocity so that regardless of the angle that we're at, we'll know with what speed the projectile leaves that launcher. There's actually two convenient features for a two-dimensional projectile that is launched horizontally. The first of which is one that may take a bit of thought to accept, but after a while, it shouldn't take that much. If you have two objects that are released from rest from the same location, in the same gravitational field, at the same height, then the time it takes for them to hit the ground should be the same. If you take one of those objects and you change its vertical velocity relative to the other, then the time that it takes to hit the ground is not the same. For example, if I drop one and throw the other one up, or if I release one and throw the other one down, those times are going to be different. But if they have the same initial vertical velocity and they have the same initial vertical height, then the time it takes for them to hit the ground will be the same. So this makes sense when you see it like this. But for an object that is launched perfectly horizontal or parallel to the horizon, the time that it takes to hit the ground is going to be the same as the time it would take for an object that were just released from that individual point. And you can kind of see this if we were to drop one and throw one out sideways. The time that it takes for them to hit the ground will be the same. So we're going to take advantage of that fact that when I release one from a height and shoot another one straight out horizontally, they both have the same vertical height, the same gravitational acceleration in the vertical direction, and the same initial velocity in the vertical direction, which is 0. Even though this one is shot out sideways with some speed, they both have 0 initial vertical velocity, and as a result, they'll hit the ground at the same time. So that's going to be convenient for us, because if that's the case, all we would need to do is calculate the time it would take for an object dropped from the height of the muzzle launcher to hit the ground, and that should be the same time that it would take for that object to hit the ground if it were shot straight out. So we're going to utilize that and get a value for the time that it takes the projectile to fall when launched horizontally. The second convenient feature for an object launched horizontally is that and first, before I go on, I should say that the time that it takes for the object to hit the ground shot out sideways or horizontally is the time that it takes for an object to hit the ground when dropped from that height, if and only if the object is launched horizontally. You can't say that that's the case for an object that's launched at an angle. That's one of the convenient features of having the object launched horizontally. So the second convenient feature is that regardless of angle, when an object is launched, if we neglect the effects of air resistance, then there is no acceleration in the horizontal direction. Vertically, the object will change its speed, whether it's on its way up and it slows down, or if it's on its way down and it speeds up. But horizontally, if we neglect air resistance again, then there is no acceleration in the horizontal direction. So if there's nothing to accelerate it, then there's nothing to change its speed. And if it doesn't change its speed, then it moves at a constant speed. So for an object that is launched horizontally, the horizontal velocity of the object remains constant even as it falls down to the ground in the vertical direction. It's one of the features of two-dimensional motion. It's like two one-dimensional motion problems all wrapped into one. So we're going to determine the time that it takes in the first part for the projectile to fall by simply calculating the time that it would take. We can do that by determining the vertical position of the launcher relative to the ground. I'm going to use a cloth measuring tape, though in your lab you should be able to do this with a meter stick. And so we will measure this value, delta y. This delta y, if you think about it, is going to be a negative value if we use a conventional axis system. We can call this our 0 meter position, and in the end, the object will land on the floor. Relative to the 0, it'll be in the negative y direction. So the displacement, and really that's what we're dealing with here, it's a vector quantity, the displacement is in the negative y-axis direction. This is, of course, for a conventional axis system. The acceleration in the vertical direction is also going to be a negative value if we utilize the conventional axis system. And it's going to be important for us to realize that both the acceleration and the vertical displacement are negative values later on when we go to insert those values into the quadratic formula. So let's go about determining the muzzle velocity for the projectile launcher. The first thing we're going to do is we're going to ensure that it is, in fact, horizontal. We can do that by using the miniature plumb bob here on the side to ensure that it is 0 degrees. So you'll make sure that that's 0 degrees. The next thing you'll do is you're going to load the launcher, and I'm using a miniaturized version of this, so yours will be similar but slightly larger. You'll load the launcher to the second click, but for this purpose I'm going to go all the way to the third. Yours you'll want to do to the second click because yours is much more powerful and it can fly much further. Before you do anything, before you launch this, you want to make sure that there is no one in the path of the projectile. You never want to look down the barrel of this when it's loaded. And the other thing is you want to make sure that the ball itself is pressed up against the bottom of the barrel. If it rolls forward, then that's going to vary your data. So you want to make sure that you can launch these as consistently as possible. Again, this ball is going to want to roll sometimes to the front. You're just going to make sure that it's pressed up against the bottom of the barrel. Now, we don't know where this is going to land. We'll need to take a practice shot. Well, I've already taken my practice shot before we've recorded this, and I've seen that it's going to land somewhere approximately in this location. For your experiment, you're going to take 5 data points approximately to determine the horizontal range for the launcher. And before you do that, you want to make sure that the base of the launcher is actually lined up with the starting point of your measuring tape on the floor. To do this, you'll use a plumb bob to get the edge location of the barrel and ensure that it does line up. In this case, the edge of the barrel lines up with the measuring tape on the floor at the 20 centimeter marker. I'm going to keep that measurement in mind because for all future measurements, I'm going to make sure that I subtract 20 centimeters from the value. So once I've made sure that the leading edge of the launcher is aligned with the start of the measuring tape that's on the floor, I'm going to use this to measure the horizontal range of it. And I can do that by, again, making sure the path is clear. 3, 2, 1. Well, where the hell was that? And 3, 2, 1. And with the carbon paper on top of your sheet that's down below, you're going to find that there's a clear impact marker. Now, what's important here is that you use the measuring tape that's already on the floor to get an idea of the scale for your paper. And to do that, we're going to take a nice marker, like for example this 2.6 meter marker, and we're going to use that to mark 2.6 meters. Anything past that, we're going to know what its value is. But the important thing is, remember that 20 centimeters down the line, we're going to subtract 0.2 meters to get 2.4 meters. So anything measured from this line is going to be from the 2.4 meter marker. So I can use this to determine that it's approximately 6 centimeters past the 2.4 meter marker, or 2.46 meters is the horizontal range. We'll do that 4 more times to get a representative value for the horizontal range. And knowing the calculated time for impact by measuring delta y and knowing the acceleration in the vertical direction, we'll have time. Getting a representative value after 5 trials for the horizontal range, we'll have horizontal displacement, and we can then take the change in displacement horizontally divided by the time that it takes to make impact with the ground to determine the muzzle velocity of the launcher. So that's the first part. The second part will be then to actually choose your angle. In this case, I'll use 30 degrees for my impact location, for my impact angle rather, my launch angle. And it's at the 30-degree angle that I'm going to have this launch. Again, you want to make sure that the vertical displacement of the projectile is measured. It's likely to have changed at this new angle. So you're going to get a new value for your delta y relative to the floor below. And this delta y, again, will be distinctly different from the one in part 1. We only used part 1 to get the velocity, the muzzle velocity of the launcher, and now that we know the muzzle velocity of the launcher, that velocity, no matter what angle, give or take a bit, will effectively be the same velocity regardless of the angle of launch. So we used part 1 to get our muzzle velocity, and now that we know that, we can then use that information. If our resultant velocity for this projectile is the muzzle velocity, then we can determine both the vertical and the horizontal components of that. And with those vectors, we'll know something about the time that it's going to take to make impact, which is determined by the vertical velocity component. And then once we know how long it takes to make impact, we can use the horizontal velocity component to see how far downrange the projectile will actually go. So once you have those values, you're going to take the values for your delta y and your acceleration in the vertical direction to plug them into the quadratic equation. That will give you 2 values for time. Since we're looking for the direction, the impact location in the positive direction, we're going to use the positive root for that equation. Knowing the time that the projectile is going to be in the air for, you can determine how far downfield it's going to go, as I said, by using the horizontal component of that. If you find the horizontal component to say, let's have a nice number of 2 meters per second. Well, if you use the vertical component to determine that the projectile is going to be in the air for 1 second, then it should make sense that for that entire second that it's in the air, it's going to travel 2 meters downfield. So you're going to have a predicted location of where that projectile is going to land. You'll then take a second sheet of paper and you'll put it on that location along with the carbon paper on top, and you'll return to perform now 10 trials. Again, make sure no one's in the path of the projectile. 3, 2, 1. It makes impact with the paper. And again, it should leave a mark. And having the measuring tape on the side will provide you a scale that you can apply to your paper, and you'll be able to determine the horizontal range for your actual projectile impact location. So what are we going to do with this? There is going to be some uncertainty here. So what you're going to do is you're going to utilize an Excel file to determine the uncertainty of the impact location using the values that you'd already measured. So this will be a theoretical impact location plus or minus some value. Then you're going to run the experiment 10 times at this angle, and you're going to get 10 impact locations. You're going to measure those values, determine the standard deviation of those values, along with the uncertainty associated with that measurement, and you're effectively going to get 2 ranges, a theoretical range and your experimental range. How do you know if the experiment was a success? Well, you'd like to see that those 2 ranges at least overlap each other. And if they do, then you can successfully state that you predicted the impact location for a projectile launched at an angle above the horizon.